for what competitions are they good and for what competitions are they bad? Does it depend on our students? Does every problem have to be unique, new, original? If a teacher, educator wants to organize an Olympiad, uh, can he or she come up with necessary problems on the spot, or should try to look for some problem somewhere? How about the internet? What kind of problems does the internet pose in Olympiad problem selection? Have we had any history on unexpected outcomes of math Olympiads that forced us basically to give brilliancy or originality awards? That is, did students surprise us with any of their solutions? And basically to share our experience of creating, collecting, and selecting competition problems. So that's what we will be talking about this afternoon. And let me tell you my two own experiences of creating problems. I've created in my life only 2 problems for math Olympiads and contests because this is just much, much harder than to actually go and win an IMO medal. That is from my viewpoint, but I guess those guys here may disagree a bit because I'm just, what's the word, flabbergasted by their complete ability to just come up with, is that the right word, flabbergasted? It's supposed to be positive. Right. With their creativity, with their ability to come up with all of those problems. So they will tell you a bit about that. To start on the right foot, we will have Sasha Soifer, Alexander Soifer, tell us a bit about a beautiful problem from the Colorado Math Olympiad, one to which he alluded earlier yesterday. So he will tell us 3 beautiful solutions about this problem. But before he comes to the stand, let me read a little bit about him. So Alexander Soifer has been a professor of mathematics, art, and history and film history at the University of Colorado since 1979. He, as you heard, founded and ran the Colorado Math Olympiad for over 20 years. His worldwide experience in mathematics competitions dates back to the 70s when he was a jury member for the USSR Math Olympiad. Since 1996, Alexander has been the secretary of the World Federation of National Mathematics Competitions and a member of the USA Math Olympiad Subcommittee. Starting in 1991, he has been the editor and publisher of the research quarterly Geombinatorics, and among his publications, as you saw yesterday, are Mathematics as Problem Solving, How Does One Cut a Triangle, Geometric Etudes in Combinatorial Mathematics, Colorado Mathematical Olympiad, and the Mathematical Coloring Book. On a personal side, he is an espresso drinking, Volvo driving, Carrie fan, and the most important event of his life is World War II, even though he was born after. Giving the microphone to Sasha Soifer.
Thank you. Okay, just one quick thing before I go to this problem. I was asked where these books can be purchased. I would have been happy to say at the bookstore near you, but it wouldn't be true. And so here is a serious answer to this question. The books that I showed yesterday, and they're upstairs, can be bought from American Math Competitions in Lincoln, Mathematical Association of America in Washington, and from this website, where you can also read journal reviews of those books. Now, the next book, this mathematical coloring book, I have no control over it because it's a Springer book, and Springer probably will advertise it more than you care to be endured to advertise it. And I want to thank the organizers, Zvezda, Paul, and Hugo, and Tatiana, sorry, for this remarkable conference. I never expected in my lifetime to see so many, shall I say, problem people in one place. Almost like an asylum for people with special problems. And now, why don't I just... The problem I'm going to talk about. Let me first tell you how I came by it, because that's a part of what we're discussing. Microphone. Okay. I was sitting on the side of Kochel Sea in southern Bavaria the summer of last year, and kids and I were tired of swimming and rowing, so I started reading a manuscript of never published book, Ramsey Theory, by Voigt and Prommel, two German mathematicians, and I found an error, and therefore I tried to find a counterexample, and that's how this problem came about. Its B part is that counterexample, and A part is simplified version of Ramsey theorem. Okay, so you just go to Bavaria and you get a problem in your hands. And here it is. Chess 7x7. Each member of a 7-member chess teams is to play once against each member of the opposing team. Prove that as soon as 22 games have been played, we can choose 4 players and sit them at a round table so that each pair of neighbors has already played. Okay? And B essentially says that 22 is the best possible. So after 21 games, we may not be able to do it. Okay? And what does it mean for around the table? It means 2 from one team, 2 from the other team, right? But all 4 games have been played. So here's a problem, and I will run quickly through first solution because it's perhaps less interesting. But the idea of first solution is to algebraically express convexity. You know this inequality, right? Quadratic average is greater or equal than mean. Oh, you can't see. Okay, and can you now? Yeah. Okay. So that essentially means that x squared function is convex. And from there it follows that binomial coefficient x choose 2 is convex, where x is not necessarily positive integer, it can be any positive real number. Okay? And based on that, we can show essentially that we have a sum of 21 summons, which is greater than 21, and so one of the summons is greater or equal than 2, and that would mean precisely that there are 2 players of one team who played both with 2 players of the other team. So that's one solution. It's a good solution, but not as good as the other are, and so that's why I ran quickly through it. We can represent the state of the chess tournament as a table 7x7, where we put a checker in the row I and column J if the player I of the first team has played the player J of the second team. So after 22 games, we will have 22 checkers. And the task is to prove that no matter how 22 checkers are placed on the board, you can choose 4 of them which are vertices of a rectangle with sides parallel to the lines of the square. So that's the problem. Okay? We'll assume that you can put 22 checkers in such a way that there are no rectangles. Then, by pigeonhole principle, there will be a row with at least 4 checkers in it. Observe also that we can interchange rows and columns because that doesn't change the property of having or not having the checker rectangle. And so by interchanging columns and rows, we can get 4 checkers in the first row in consecutive columns from the left. We consider 2 cases. First, there are exactly 4 maximum rows, checkers in a row. Then, as you can imagine, in every row below the top, to the left from line L, there would be at most 1 checker, right? Therefore, to the left from L, we will have at most 10 checkers. 4 and 1 per each of 6 rows. 10, right? Therefore, there are 12 on the right. Nothing here. So we can create a column with 4 consecutive checkers here. And if there are 4 consecutive checkers here, it means in this 1 by 4 there will be at most 1 checker, and here at most 1 checker. So 10 plus 6, 16, and 6 checkers remain, which means this area is completely filled up, and that contradicts the assumption that there is no checkered rectangle. Second case, there are 5 or more in a row. Then again, the rows below to the left from L contain 1 checker at the most. Therefore, in the right 2 columns, we can pick one with at least 5 checkers, only at most 1 here, which means 17 checkers. So 5 have to fit in D and E, and that's hard to do. Done? So that's the second solution. And I think it conveys the spirit of an Olympiad the way I understand it. But here's the third solution, and then we'll go to B. We create a function. If we have k checkers in a row, we can compute k choose 2 binomial coefficient. And now, for each of the 7 rows, we compute that and add it up. That will be our function C of P, where P is a placement. Then observe, if there is a row with 4 or more checkers, there will have to be a row with 2 or less checkers. And by moving 1 checker from 4 or more to 2 or less, we reduce this function of placement, C of P. So let's keep reducing this function. What will be the end? The end will be when 1 row contains 4 checkers and all others contain 3. And function for that is 24. Now, I'll tell you a secret. 24 is greater than 21. What's 21? It's a 7 choose 2. Therefore, some of the pairs will be repeated. But this is what it means. If a pair ij appears in one row and the other row, we're done. That's this rectangle that is forbidden. And that completes the proof. Now, the B part. We need to construct a counterexample that shows that 21 ain't enough. Well, here's what I do. First of all, let us glue a cylinder out of 7 by 7 board, and here it's one diagonal covered by checkers. So my placement of 21 checkers is as follows. We just put checkers on diagonal 1, 2, and 4. And blank ones correspond to the solid ones on the cylinder, right? Now, assume there is a rectangle on these 21 checkers. But since there are only 3 diagonals and 4 corners, 4 checkers, 2 of those checkers must be on the same diagonal, say here and here. But that means that our rectangle is by necessity a square, which is a surprising step. But if it's square, then 2 other corners of the square are symmetric to each other with respect to this diagonal, which means 2 of the diagonals must be symmetric to each other with respect to the 3rd diagonal. And it isn't the case, because if you look at these diagonals from above, they're diagonals 1, 2, and 4, and the distances between them are 1, 2, and 3, and we're done. That's not all what I wanted to tell you, because I have 3 more minutes. I have to tell you that, remarkably, this placement of 21 checkers is unique up to interchanges of rows and columns. Doesn't look obvious, right? Well, just think about it. We have 7 rows and 7 columns, and we can think about them as 7 points and 7 lines. And we get a finite projective funnel plane. That's what it is. And this plane is unique, which is easy to prove. And that means precisely that the placement of the checkers is unique, up to interchanging of rows and columns, which is the same as renumbering the players on 2 respective teams. That's it.
I have. Yeah. Okay.
Why is the absence of a checkered rectangle? Why does it mean the same thing as that that must be the block scheme must be the same as the projected plane? I'm sorry. Say it again. I understand that there is only one finite projected plane with those characteristics, but why does it have to be? Why does the scheme has to be a finite projected plane? How does it correspond to the absence of a checkered rectangle? Well, we must put 3 checkers in every row, in every column. Now, let us call every row a line, and every column the point. Okay.
But I have a question. So that was an actual problem from the Colorado Math Olympiad. What were the results?
The results, you mean in terms of success? 15 students found a counterexample for the B part, and 1 student found a solution for A part. A junior. Oh, just under 700. Method. Yes. It wasn't as sleek, Paul, because, you know, I simply had more time than they. After all, it's my problem, you know. But yes, it was. In fact, many of them, most of those 15 who found counterexample, used this representation as 7 by 7 square table. They may not have called it checkers. They would put ones or ones and zeros. But they did find that this is a convenient way to describe the problem. And they did formulate that the task is to show that rectangle doesn't exist, which I think is substantial advance. You know, to translate the problem into easier visual language. So, just one plus. You know, a problem that started from Ramsey theory and jumped into a chess tournament and very much Olympiad type problem suddenly ended up on finite projective planes, once again going into serious mathematics. And I think it's nice when we can have this interplay between mathematics and competitions.
Thank you, Sasha. In fact, one of the two problems that I created came about in a very similar fashion. When I was doing some serious math, then I realized that the problem can be translated into Olympiad terms. It was given to the second Bear Math Olympiad and ended up on the t-shirt, the back of the t-shirt. And then later on, I realized there is more math associated to it that I did not know. So that's actually, I call such a problem quite a successful problem for us as problem creators and for the students too. Our next presenter is Kiran Kedlaya, who is an assistant professor at MIT working in algebraic geometry and number theory. His involvement with Math Olympiads dates back to 1990 when he first represented the US team at the IMO, and he went on for 3 years. Okay. Since then, he has been a grader and instructor at the Math Olympiad Summer Program, a member of the USMO committee, deputy leader of the US IMO team, a member of the executive committee, and a head coordinator of the 2001 IMO in Washington, D.C. Of course, he was a lecturer at the Berkeley Math Circle while he was here. We couldn't miss him. An editor of the American Mathematical Monthly Problem Session, and he also co-authored a book on the Putnam exam with Björn Poonen and Ravi Vakil. His other interests include games and puzzles, choral music, and photography. Kiran?
Okay, thank you. Thanks for the invitation to. I'd like to thank the organizers for the opportunity to speak. Let's see if I can get this full screen. I also have to apologize for the lowest tech PowerPoint presentation you'll ever see. It's just a convenient way for me to sort of put on the page everything I'm going to say, just so I get to it all. Oops, that's. So I have a few points that I'm just going to run through, and hopefully if we have time to have a little back and forth at the end, some of these might spur discussion or questions. First thing I wanted to mention is, where do my problems come from? I should point out that most of where my problems go tends to be the US Math Olympiad. I've had problems on most of the USMOs for the past 10 years or so. And certainly when I first started doing this, this was before I was really a research mathematician, so I was mostly trying to construct problems. I would sort of take problems that I had enjoyed or had seen before, fiddle around with them, see what happens, just sort of explore. I should point out that I hardly encourage this as an activity for students to get involved in. The proposing of problems, as may have been mentioned earlier, is an important bridge between solving little self-contained problems and the open-ended nature of research mathematics. Trying to sort of find good self-contained problems is a useful thing, and I learned a lot in doing it. You know, in geometry, you have a similar thing where you sort of draw pictures and move stuff around. But nowadays, I spend a lot of my energies conducting my research as a research mathematician, and a lot of my problems come from that in various ways. I sort of try to keep an open mind about what I'm doing, sort of the way Sasha did with you know, his paper he was reading. You know, if something comes up in my work and I can see a way to pull it out and make it self-contained, I'll try to condense it into a problem. I also look actively for good ideas that can be appropriately condensed in, for example, papers, you know, in combinatorics. It's a good place for them. I also tend to make it known among my my mathematician friends that I'm always looking for good explicit problems, and I get great suggestions from colleagues. You know, I had a problem last year on the USAMO that was actually a problem that was asked to me by my longtime friend and colleague and former Olympiad partner in crime, Lenny Ying. He actually had this problem that was coming up in a topology calculation, and he didn't know how to do it, and I solved it, and we decided it was a good problem, and made it onto the exam. And there was even a brilliancy prize given for a special solution which was simpler than the one I had come up with. I was completely shocked to see it, so it was a very rewarding process there. Yeah, so keep an open mind, keep my friends in the loop. That's how do I evaluate problems? One thing that we emphasize among people evaluating USAMO problems, you know, so zooming and T2 and so on, we'll see that this rings true, is you always have to put yourself in the position of, you have to put yourself, so to speak, on the other side of the desk. You can only really tell how difficult a problem is if you actually try to do it yourself and either succeed or fail, find a solution that was not the original intended one, and so on. It's very easy to misjudge things when you don't really try to solve the problem yourself. Of course, you can't judge your own problems this way. You have other people do it for you. This is an issue at the IMO when problems are proposed and not everyone actually takes the time to try to solve them. They sort of misjudge the difficulty. Difficulty, of course, has two components: the ideas and the techniques. And I personally tend to think that good problems should balance some of these. There's some variance in opinion. I've noticed a lot of problems from the Russian Olympiads tend to have more ideas and somewhat less technique, which, you know, is a stylistic thing, but I think matters. They both matter. Also, the Putnam problems tend to be somewhat more condensed because you're given less time to solve them. Contextual issues just means you can't see it because it's cut off, but things like how hard is the exam overall, what's the balance of topics, do you want to repeat a topic that you just used on the same exam or in another exam that students will have seen recently, maybe you don't. Things I look for when I sort of do this evaluation is difficulty, obviously. Originality, of course, is a mysterious thing because there's no new thing under the sun, really. I like to describe the set of problems as an infinite set, but it's compact. Every problem is actually nearby to some old problem, and you know, you just try to get as far away as you can from problems that are A, classic, or B, sort of recent. I'll come back to where people are looking for problems to train on in a moment. Do your homework. I'll mention that. I like things that are sort of elegant and simple to state. The solution should have some ideas that are really key to describe. I stole this quote from Bruce Resnick, who wrote an essay about constructing for the Putnam. He was on the Putnam Committee, which Ravi and I included in the Putnam book. He says that a Broadway composer tries to write a tune so that even if you don't pay much attention to the plot, you should come out of the show humming the tunes. Well, ideally, you should come out of an exam humming the problems, and that's sort of that's what the goal of these simplicity and naturality things are. Flexibility is that ideally there are multiple approaches that use different ideas, or at least different ways to interpret the same ideas. As we saw, there are several ways to attack Sasha's problem, which makes it a nice problem that way. There's an issue of how to do your homework. Well, homework got a lot harder when the internet really took off. There were traditional resources that you assume that students study. There are the books, some of whom are written by people on our panel, the standard exams, the USAMO, IMO, Putnam, and so on, and things like Crux Mathematicorum. Now the internet means that things like national Olympiads and the IMO shortlists and so on are much more accessible, and there's like the Art of Problem Solving website where students really are networked and are sharing a lot of information. So you have to do more homework to see whether your ideas are really new. There was an example from last year's IMO where one of the problems, actually the solution could be found on the internet. It was sort of a natural enough problem. There was this problem about sort of hexamonos tiling rectangles, and in fact it was so natural a problem that somebody had actually had the solution on the internet and just nobody realized it at the time. The last thing I want to do, and I'll have to really make this brief, but I hope this will touch off some more discussion later, is some thoughts about documenting our work. I mean, one of the parts of writing problems is writing about the problems when you're done, presenting solutions that students will see. So just a couple of thoughts. One thing we use in the Putnam book, which I like, is the idea of having short hints that the students can look at before they actually read the solution, just to get some, you know, that way they can try to solve something even if they haven't quite grasped the key idea by themselves. What I call cubism, which I just mean sort of presenting multiple angles on the same thing, sort of in the same place. So multiple solutions, as we saw, and alternate interpretations of even the same solution can look extremely different. So it's sometimes useful to have them. Try to show where the solution came from rather than just writing it in the sterile. I mean, it's good to present a self-contained, you know, mathematician-style solution, but the, you know, approach things also from the way the solver would see them, point out how you got there, so on. And the last thing, which also touches back with Sasha's presentation, is to make connections. I mean, one thing that we did, that we sort of made an effort to do in this book, what we wrote about the Putnam, Ravi and Leon and I, is to suggest whenever we presented a problem, we tried to avoid having it just be a problem. We'd like to have it connect to related problems, techniques that are used across several problems, or ideally even real mathematics. We had this phrase on the back cover that, you know, we hope these problems, which are sort of toys, serve as an entree to beautiful and powerful ideas. So we were hoping that we would really forge some connections in the students' minds between these toys, these sort of self-contained problems, and kind of the real work that you know, a lot of us do and really appreciate, and we're hoping that we're guiding our students in that direction and trying to use the problems as a way to do it. So I should stop there.
I'll change the style of our sessions, as you have seen. One very good question for Kiran. No good questions for Kiran? Well, let me explain one technicality that he mentioned in his presentation. That the IMO this summer, no one noticed that the solution to a certain problem was on the internet. You realize that while the problems are being selected, the jury is sequestered. So we have no supposedly connection to the outside world, including internet. So the duty of checking out such blunders falls onto the shoulders of the committee, that the problems committee for the IMO, and now their job is even harder than before without the internet. You'd think it's easier, but it's actually much harder.
The USMO committee has to do a very similar thing.
And the USMO committee too, yes. Okay. So next we go to Ravi Vakil, from originally from Toronto, Canada, but presently from Stanford, just next door. He received his undergraduate degree at University of Toronto, where he was a 4-time Putnam competition winner. After completing his PhD at Harvard, he, with the same advisor as myself, he taught at Princeton and MIT before moving to Stanford, where he is a tenure-track assistant professor. His field of research is algebraic geometry, with connections to nearby fields including combinatorics, topology, number theory, and physics. He is an American Mathematical Society Centennial Fellow, a Sloan Research Fellow, and received the Presidential Award PCASE. Is that how you say it? Okay. He has long been interested in teaching mathematics through problem solving. He coached the Canadian team to the International Math Olympiad from '89 to '96, and he himself was the star of the Canadian team for a whole decade, so to speak. Runs a weekly problem-solving seminar each fall at Stanford, and has co-written 2 books on the subject. I personally met Ravi, I believe, at the IMO in Cuba in '87.
Great. So I'd like to thank the organizers again. And I should just mention that this is one of the great things about math circles, math competitions, things like this. I went to an ordinary suburban high school where, again, I had no peers, but not a negative environment, as I gather many schools have. And so it was just a chance to go to these competitions that gave me, that for me was the entree into higher mathematics, and gave me a chance to meet people like Zvezda, for example, that many years later on I was surprised or not so surprised to run into again. And having met people early and young makes a big difference in these things. So I'd like to first of all start by mentioning this book with Kiran, which we and Bjorn Poonen, which as Kiran did say, we meant as kind of a manifesto, because I think we perhaps don't fully, we largely agree with the way the problem community views problems, but we have many disagreements with this as well, and we put them implicitly in print in how we decided to present them. So rather than repeat the things that Kiran said and that other people had said before and say something coherent, I'll instead be incoherent and just say a whole bunch of things that I think need to be said about problems, what are good or what are bad, and why problems in general. So first of all, I should say that what's a criterion for a good competition? What are good problems on a competition? Well, you have to first ask what's the point of the competition. I've heard a few statements here that suggest that people see competitions differently than I do, for example. For example, what's the point of an exam? You could say the point of an exam is to get an A, or to answer the questions, and see the questions on the exam as ends in themselves. And I think that's completely the wrong way to see an exam. When you set an exam, that's not what you're thinking. It is true that with an exam, perhaps you want to run through the material, make sure people have a facility with it, but you want to test that they're able to understand what's going on. But really, the point of the exam isn't what's happening in that hour in an exam at the end of the course. And what matters is what you're provoking students to do beforehand and what you're provoking students to do afterwards as well. So the point isn't that hour. And in the end, what's a grade on an exam? Well, it means what it means. If someone gets an A in a course, it means they got an A in the course. Does it mean that they can't be a mathematician if they didn't get an A in the course? Well, that doesn't mean that at all. And ditto for a competition. Some people, so I think the point of a competition isn't to select the winners. This is a fringe benefit perhaps for some purposes, but that's not the reason we do it. And as an example, I wanted to mention that I'll say we started in a little bit, but we run the Putnam competition at Stanford University, and we changed the philosophy. So I arrived and did things a little bit differently. We used to traditionally have 5 or 10 people taking it, and they would be the hardcore people and they wouldn't get much out of it. And instead, we have now typically around 60 to 70 or over 70 students taking it. And you have to ask why they're doing this. Since these are students, it's the weekend before their final exams. They should be studying for their exams. And it's not because they think they're going to win. Stanford has never won. There's never been a Putnam Fellow from Stanford. There won't be anytime soon. And I don't tell them this, but this is, but I do tell them right away that the point of this is, so I tell them the median mark on the Putnam out of 120 possible points tends to be 0 or 1 point. And these are students who've they're used to being at the top of their class. You can ask, why would someone who's used to winning everything do something where they know the odds are that they're going to get 0 or perhaps 1 out of 120 and spend 6 hours doing math problems on a Saturday before their final exams? And the answer is that they're not who you think they're not the kind of people that you think that they are. These are like students anywhere, and they're open for a challenge. They like math, and they want to try something hard. It's like running a marathon. I remember being at the end of the New York City Marathon, not competing, but watching them. And that was the most inspiring sporting event I've ever seen, because I missed the winners, but people were making it to the end, and it was such an achievement for them to do this that the crowd was going wild whenever anyone would come by. And if someone was tired, people would cheer them on and get them going. And so for them, it's like Mount Everest. It's because it's there. They want to try their chance. And one of the nice things, I don't think this is good for competitions in general, but this one, the median is very low. And in this case, it's a good thing, because there's no shame in not getting anywhere. You want to try the problem, see how it works. If you crack a problem, fantastic. If you get somewhere in a problem, that's just amazing. But I'm impressed with people for just showing up and wanting to do math. And I think that's really the point of it. And again, the secret behind it is beforehand, we run a quote Putnam problem-solving seminar, and that gets people in the door. So for me, I don't really care how they do in the Putnam, but it gets people. If I said math club, they would not. We have around 120. We aim for around 2% of our student body being involved with this sort of thing. If I said math club, they wouldn't come. So I call it a Putnam problem-solving seminar. They hear about this hard thing, and they turn up, and and it's an excuse to do math, and that's what they're there for. So I think that's the way in which you should see this is what the problems are there for, not for what happens on the day, but for what happens afterwards. So when you have, actually I haven't been watching my clock, so warn me when I'm getting close. For example, when you have an exam in many colleges now, old exams are available, and so hence exams should be seen not for what the students don't think just the students who are taking it. Think of future generations that will look at it, and it will be a study device. It'll suggest, here's something interesting, here's something to know. And so a good problem is something that, as Kiran had said, quoting Bruce Resnick, is that you leave humming a problem. So it's good to have on a competition a problem that they will leave wanting to tell their friends about. And it doesn't matter whether they got it or whether they didn't get it. It should be just something that they find that they find fascinating. There should be something, so there are other questions when you're setting something like this. Everyone should get something out of the experience. So I don't think that, I think the weakest participant should be able to get traction on a problem and really make contact with it, even if they don't necessarily solve it. They should enjoy the experience and have a good experience with mathematics. And contrary to our prejudices about how younger people think, they don't need to answer all the questions to feel happy. If they grapple with something, they can enjoy it and they will enjoy it. Conversely, no one should get perfect. So if someone's worrying about the last grade on an exam, that's not so good. So there should be something for everyone. And when you're setting a bunch of problems, you really can address many audiences simultaneously. I think the solutions should teach not just the people taking it, but also future people. And in particular, solutions should be available afterwards. About where they should come from, I do think if you're starting up a math league, or feel free to steal problems from other sources. So students have access to all these things, but they're not going to be, know your audience, know what they're going to know, and they're not going to be memorizing everything on the web. So in that case, the web is your friend, and more, I guess, other friends are sitting here in the audience, and you can just take problems from other math circles, if you're running a math circle, if you're running competition, take it from a math league elsewhere, and people will, the good thing about this is it's not very competitive. I mean, we're not competing amongst each other, and secretly our school students aren't really competing with each other either. So just trade things, and I think there should be nothing wrong with that. Two things that fit in with the manifesto is there should be connections to deeper material. I do think that you should, okay, so 1.5 things. So connection to deeper material, I deeply admire the Eastern European model, which has produced such astonishing successes. And I do think that senior mathematicians talk to junior mathematicians, talk to graduate students, talk to undergraduates, talk to high school students. And we've got a disconnect somewhere in between, which means that the problems we come up with are less interesting. And my last thing is a plea for certain types of problems. We've seen a lot of combinatorics problems, and Dan Fried, who couldn't make it right now, but is professor at Austin, had asked, why do we have so many combinatorics problems and so few analysis problems? And I'll submit to you that I think I'm a big fan of combinatorics myself. I submit to you that it's laziness on our part, that we should try hard to set people up to think about the ideas that they're going to see later on in college. And so I think we should work hard to try to think of some good problems and different topics that really test ingenuity. Okay, thanks.
Any question to Ravi? Walter? Is that course for credit?
No. No, it's they get nothing for it. It's completely. They get pizza, but they get no credit, nothing on their CV.
So basically, what I learned from Ravi is that reverse psychology works on students. You're gonna get nothing for the course. Well, pizza. You are going to probably solve 0 problems. So as long as they're doing reverse to what their teacher says, they're going to do well. And to that end, 4 of my Mill students this year went to take the Putnam. And the math major at Mills is very, very small. So that probably contains something like 40%.
I want to have a question for Ravi. Maybe I can speak loud enough. You made a provocative comment, I think I heard it right, that Stanford will never have a Putnam winner? Could you explain that? Why? Seriously.
No time. I mean, the odds are people have good or bad days, and the odds of clicking, you need to have. If you want, our student body has at this point a lot of really good people, and I think at some point soon we're going to start to attract a few of the people who are off the scale. And I think that the off-the-scale people are just going to start to come soon, but they're not in the pipeline right away.
Our next speaker is Joshua Zucker, who was a participant in Dr. Ross's summer number theory program and the Math Olympiad summer program. He studied math, physics, and astrophysics at Stanford and UC Berkeley before becoming a math teacher first at community colleges, then at the educational program for gifted youth at Stanford, and finally at Gunn High School and now Kedlaya School in Palo Alto. He has been involved in local math competitions as well as the American Regions Math League and is now a problem writer for Math Counts. He also enjoys volunteering for the online math forums, Ask Doctor Math Service, as well as juggling, bicycling, and spending time with his 2 sons.
Thank you. Yeah, I mean, as he says, Stanford is not going to produce a Putnam person anytime soon. I mean, I went to Stanford, and I was the best math student when I was there. And, there was nobody like the rest of this panel going to Stanford at that time, and I think still hasn't been. Anyway, so this is, I think, something about what the summary of what some of the previous speakers said. I made this up before hearing their talks. But they said, a good problem should be beautiful, should have ties to serious mathematics, natural, original, simple, elegant. I think these are all good criteria, but my criteria for a good problem are a little bit different. A good problem is one that I can do. That's my opinion. Or at least I think I can do it. Or at least I think I could maybe if I worked at it for a while. Some of the most beautiful problems are problems I can look at and say, wow, that's beautiful, and stand there and watch it for a while, and I still think it's beautiful after a while, but if there's not something I can do about it, I find it kind of frustrating, even if I do admire the beauty of the problem, even if I admire the beauty of the solution when somebody hands it to me. I need to be able to maybe play with some special cases, at least feel like there's something I can do with a good problem. So that's my opinion about problems. They don't have to be, I don't know, I don't have quite the same lofty goals, maybe because problem writing is too hard to always aspire to that, but I think I'd like to have a problem that I can do. So a good contest will have to have some good problems, but I think there's some other factors that I think are lacking in a lot of the Olympiad-style competitions, the Putnam or the USMO or the IMO, which is that there's no teamwork. You say, well, we're part of the IMO team. That talks about all the things you do before the contest, and it talks about all the things you do after the contest, but it doesn't talk about any of the things you do at the contest. And so I really like contests, like the ARML contest, where there is some genuine part where students really work together on something. And it's great that the preparation always involves that sort of thing. But certainly when I was in school, I was very isolated from everybody else. And I had these brief experiences where I could do some work, some teamwork. But I think contests with more teamwork is a good thing. Another nice feature of, I think, some good problems is ones that are designed to help you learn that process of how do you get started on a problem that's too hard for you. And the way you do that, I think, at first, is by handing them the parts. Saying, well, first just do this little numerical example. Really, it's not scary. It's okay. You can do it. Then you build up a little bit harder, and finally you're asking them to prove something real. Or like at the Ross program, where you're given the numerical examples one day, and maybe you come up with some conjectures, and then you're given the theorem, or maybe the not quite theorem that you have to fix up a bit the next day. Something where you see the student gets handed a little bit more of those parts. I think it makes a very nice contest. So here's a sample problem which I used on a local math contest some years back. Given a cyclic n-gon, prove that the sum of the n radii of the n-2 triangles you get when you triangulate is the same. So it's kind of a pretty problem. There's lots of easy special cases like, a triangle, very easy special case. Square, pretty easy. You can do lots of fun doodling. So even if you have no idea how to do the problem, at least there's something on your paper in front of you. That's a big plus. And it gets hard fast enough. Once you get past square, even to pentagon, there's plenty to think about, even if you have a regular pentagon or something. Then what about other cyclic pentagons that aren't regular? When I tried using this problem in actual contest, however, it turned out not to be quite as good as I thought. What's an n radii was one of the questions I got. When you do the easy special cases like the square or something, does that really lead you any closer to solving the problem? If it doesn't, if you say, well, here's this special case I can work out, but it doesn't give you any clues about what's going on in general, it's not so helpful to have that feature of the problem. So how do you make it better? Well, what I did on the contest was I broke it up into a whole bunch of parts. And the first few parts were for people who maybe their high school geometry class wasn't so good. Tell you a little bit about what is an n radius. It's the intersection of the angle bisectors and how come and why do all these things work. Finally, as you're getting very close to the end where you're finally going to be asked this relatively nice problem, ask a problem about a triangle that probably they can do and that gives them some clues about a method they can use to solve the real problem. So in other words, sometimes people need a little bit of help getting started on some problems. And I think for a lot of contests, when you're not writing for the Putnam or the IMO, you need to take into account a lot more with your audience and step them through the process of how do you become a good problem solver. You try some simple examples. You use those things. eventually you lead up to something close to a solution. So you want to give people challenging problems they can work on, which are a lot better, I think, than just beautiful problems they can look at. So nowadays I'm a problem writer for math counts, and you have to have easy entry into a math counts problem because on a lot of Olympiad problems, I'll spend the first 15 minutes just reading the problem and trying to figure out what exactly it is that I'm trying to do. In math counts, the problem's over in a minute. If we have a really long, tough, challenging problem, we'll move it over to the team or the target rounds where they have 4 or 5 minutes to work on it. That's some sustained effort for a 6th grader. You can put in some nice problems that have interesting generalizations, but I think the best part of the whole process is that you can write problems for the school handbook. There's all kinds of advantages of this. When you've got that pretty nice Olympiad problem, but it's hard to come up with a nice, clear, concise, unambiguous statement, and so you're worried that people will misinterpret it and then argue with you about whether they should get credit for it, you just put it in the handbook. No problem. They can argue with their teacher in their school about whether it's a good problem or not. But the main thing is you can give problems that don't have to have quite the same time pressure. You can write about for a few of the problems, you have to write a nice little paragraph explaining what makes it interesting, making some of those connections explicit. So I think the idea that you have to have solutions that are published along with the problems and really show people where to go with them is a really important idea. This school handbook gets into the hands of tens of thousands of people. So if you write a problem, which sadly few math counts problems are even, I can say this as a writer of them, most of them are junk. Most of the problems I write are junk because they have to be solved in a minute by 6th graders, right? But plenty of the problems can be interesting too. So you can write the occasional interesting problem, you can sneak it into that handbook, you can write a nice little paragraph to go with it about the solution, and count on the fact that tens of thousands of kids out there are going to get their hands on it, which is a good feeling. When you write for math counts, unlike when you write for, say, the Putnam or the USMO, you're catching a lot broader audience and showing them a little bit about what are the things they could think about than the pre-algebra they're learning in their school classroom. And you can slide some interesting and challenging math into the schools without scaring the teachers too much. Because the math count stuff is mostly arithmetic, algebra, stuff the teachers are relatively comfortable with, not Olympiad problems where you're going to be scaring away a lot of the teachers. So I think one of the good features of math counts being aimed at the level it is that the teachers are overall, in general, less afraid of these types of problems because they can mostly do them. So I'm hoping that by writing for math counts, I can bring some of these ideas of problems you can do into the classroom, and then maybe for some fraction of them, you can build to problems that are really quite a bit more challenging. So thank you.
Any questions for Josh? No questions? Yeah, there is.
Forgive me for asking a silly question. You gave that hint about finding the sum of the distances from the circumcenter to the vertices. Yeah. Wouldn't that just be 3r to the sides? It went by too fast. Thank you.
I'm glad we clarified this. Any other questions? Ted?
So a lot of people here have talked about the benefit of math competitions in terms of leading people, or math circles, in terms of leading people to be research mathematicians. And you've alluded to, and I'd love for you to go on a little bit more about the benefits of these things for people who aren't going on to be research mathematicians.
Well, look at me. I'm not a research mathematician, but I think all these things were very beneficial for me. So I'd certainly use myself as one example of what can happen with these kinds of competitions. But I think, who is Math Counts founded by? It's founded by engineers, not by mathematicians. And I think that really shows in the kind of stuff they want to do. They want people to learn about proportional reasoning. That's a basic thing. That's fundamental. Everybody should understand proportional reasoning, especially engineers and mathematicians, but especially engineers. That's a great topic to have really heavily covered on a contest for middle school students. And I think that when you start to talk about that kind of thing, you can say, well, in the curriculum, this is something that we don't do enough creative stuff with. It becomes, well, you have your chapter on proportional reasoning where you sit there cross-multiplying fractions a bunch, but it's not something that you connect to all the different types of problems where it can really be used. And Math Counts is one source now of a bunch of other problems. So I think those kinds of skills are not just the ones that research mathematicians need. I think teaching people about proportional reasoning is a good end in itself for every student, whatever their career is going to be. It's something they can apply in their thinking. And so probably I'll talk more about that later when I talk about bringing these things into the classroom and what happens there. But yeah, my feeling is that Olympiads are quite a different thing than math circles, which in math circles can be quite a different thing from contests like math counts. And I think they all have their place in this job of getting people to think about mathematics a little bit more than just as a bunch of algorithms that you memorize and follow, which is really the point, I guess.
Okay, thank you. So let's move to our next speaker. Richard Rusczyk is, well, you've heard about him today a lot, but let me just say a few things that he did not mention. He was himself a participant in the National Math Counts and a 3-time participant in the Math Olympiad Summer Program and a USA Math Olympiad winner in 1989. He graduated from Princeton in 1993, helped inaugurate the ESPN's Sports Figures program, and worked as a bond trader, as he said today, at D. Shaw and Company for 4 years. And I guess the only other thing I had to say is that he's one of the sportscasters for the National Math Counts competition. Is that right? You did not mention this earlier today.
Thank you. First, I'll start off talking about how the most effective way I found to write good problems was when I was coming up with the idea for the Mandelbrot competition, I went and got Sam. And that worked really, really well. And I'm here now. And yeah, he's here this time. And that worked well because he did a lot of the things that Josh just described. When he built a team competition, and we would give the subject ahead of time so the kids would have something to prepare for, and he would take some problems that sometimes he even wanted to propose them for the IMO. These were really hard problems, and he would break them into 4 or 5 parts and make really nice problems. For the other half of the Mandelbrot competition, we would have an individual competition, which was a series of short answer problems ranging from kind of easy AMC to moderate to difficult AMY. And I had a really good strategy for coming up with good problems there. I would ask the third person in our group, Shandor, to write hard problems, and Shandor would send me a bunch of problems, and 5 or 6 would come without solutions, and I would send them to Sam. And half of them would come back with solutions, and the other half would come back rewritten as better problems with solutions. And I've seen this kind of way of going about writing problems very effectively over the last year as I got involved in the USAMTS, because I see that this is how George comes up with really good problems for the USAMTS, is he has a network of really good problem writers and people who can evaluate problems and tell him, tinker this, change that, and move this thing over here. So find good people to work with. That's what I did. Now, when I first got involved with math competitions, or when I first got involved with this panel, I thought about, well, we're just going to stand up here and all agree with each other. But then I got thinking about it more, and I thought about what were the contests that I've been involved with or the ones that I've been involved writing that were bad. And the problem wasn't that they were bad problems. I generally, well, I guess I write some bad problems, but usually the problem wasn't that I wrote poor problems. I wrote good problems, but they were still poor contests because I didn't understand 2 things. And the 2 things I didn't understand is who was going to be taking the test, and the second was what is the goal of the competition to begin with. So when I start thinking about that, one thing that we haven't talked about a whole lot here, and we touched on just a little bit there, and I want to talk about more now, is what's our goal? Why are we writing these math competitions? See, I think we as math educators have a much bigger goal than just developing the next generation of mathematicians. And maybe this isn't the room to be saying that in, room full of mathematicians here, but we are the people who are supposed to be training the next generation how to think. And there are other ways to do that, but math is the best way. And I think at least on that we can all agree. So we have to do the heavy lifting here. And math contests are a part of that. It's not just about building the next generation of mathematicians. We're also building the next generation of doctors, of lawyers, of engineers, of everything. And these professions don't all require Olympiad level problem solving skills. All right, some of them, when I go in for surgery, I want Ravi and Kiran to have designed the surgery. I want these people that can do the deep thinking, but I want the math count speed champion doing it. No offense, guys. So, and some of our competitions do this pretty well. And that's like, I'd say math counts does this pretty well. they're training that particular skill. Granted, we don't think it's that as important as the deep thinking skill. All right, and I agree with that, but there is some merit to it. There is some merit to what they're selecting for. And there's another thing these portal programs are really important for, and I think it's again something we tend to overlook somewhat, is exactly what I just called them. They're portal programs. They're bringing the kids in. And if you have an Olympiad level program that you want to be able to get lots of kids in, if you can go into the schools and get them to use it, that's great. But it's hard. Math counts and various state and local competitions have solved this problem. They're able to get into the schools a lot better than we are. And that's because one thing they really understand well is their audience is not just the students. The audience is also the teachers. So what Math Counts does, and Josh just talked about, they build materials for the teachers to use. They give hooks for the teachers to use it in the classroom. And that's something that those of us who design harder programs have to do better. And one thing Sam would do sometimes with the Mandelbrot is he would even write a paper for the teachers to use or the students to use to prepare for the competitions. But those of us who are preparing these intermediate and more advanced level programs, we have to do this better. Because, like it or not, even we have the internet now. That's great. We can reach a lot more people, but the schools are still the best portal to reaching more and more students. And we heard earlier today, you said you went to your middle school teacher, and your middle school teacher said there are no more competitions, right? That's where the students go first. That's where the teachers go. The parents go first. They ask the teachers. So we have to build hooks for the teachers as well. And this is how we can guide ourselves to build good problems and build good contests. They have to be a small step away from what they're already experienced in doing. And then they have to give a step going out in the other direction. They have to point the student in a direction afterwards. And for the teachers, it has to point them as well so that they can direct the students somewhere. And I'm getting the time signal. So I'll go ahead and summarize with, no matter what level you're creating a problem for, I think the best measure of any competition or any problem, it's already been talked about a little bit today, is the student still thinking about it later?